First, we're going to talk about strong acids and bases, and then we'll talk about weak. And strong acids do not have an equilibrium, so you might wonder why we're showing them in this chapter. Well, the reason why is because water is always there, and water has its own equilibrium. So anyway, let's consider the strong acid and see how that affects water. When you have hydrochloric acid, and it is one of the strong ones that were on our list of 7 strong acids, so since it's strong, it totally ionizes in solution. And notice I don't have the arrows going both ways. It totally breaks apart. So because it totally breaks apart, the hydrogen ion concentration, if you start with 0.2 molar hydrochloric acid, the hydrogen ion concentration will be this same number. Okay, remember, and I put this little thing over here because water does have hydrogen ions floating around even when there's not an acid there. It's just that in water it's a very small amount, and those concentrations are equal, hydrogen and hydroxide. Okay, so this concentration, when you put hydrochloric acid in water, the part from water doesn't matter. It's very small compared to the hydrogen ions that come from the acid. Okay, and so in this one's pretty obvious. In this case, what about the hydroxide ion concentration? You might think, oh, it's an acid, it doesn't have any. But it does. It does have hydroxide ions from the water. Water is always there, and it's always in its equilibrium, and it has its equilibrium constant. And so what happens is, if you do something to increase this, it's kind of like a common ion actually, right? We put in this bigger number here versus the 1 times 10 to the -7th, and that makes the hydroxide ion concentration decrease, but it's still there. So if we solve for hydroxide with this, we're going to get okay, so this was our Kw. It's always true in aqueous solutions. So when you add an acid, you make this one go up and it reacts the other way, and so this concentration will drop. When you add a base will make this one go up, and so it'll react, Le Chatelier's principle, so this one will end up dropping. Let's look at another example with water and adding a base this time. So here's water's reaction that it does all by itself. In pure water, these concentrations are very low, so this is happening without a base. But then when we add the base, we're adding this is a strong base, which means it ionizes completely. So when you add that 0.015 molar, that's a lot bigger number than these. You're essentially dumping 0.015 molar hydroxide ions into this water. And so what is this concentration going to do? Because this is what I was saying, this amount doesn't matter anymore once you add all of this. Okay, so what is our hydrogen ion concentration going to be? Well, we know that this first equation with our equilibrium, we know that this number is equal to the hydrogen ion concentration times the hydroxide ion concentration. And so we can plug in our new hydroxide ion concentration that we have. And just divide, and we can get our hydrogen ion concentration. And so by adding this hydroxide ion, it caused the hydrogen ion concentration to decrease because it was 10 to the -7th. So just like I was saying, this is kind of like, it's a law. That's the way you could think about it. anytime you have an aqueous solution, the product of these has to be 1 times 10 to the minus 14th. And so if you do something like we did here to dump in a bunch of hydroxide, this one will decrease. Again, it's Le Chatelier's principle. If we look at this reaction and we add hydroxides, the reactions will go that way. The reaction will go that way, which will mean this concentration will drop. But anyway, so let me answer this question down here at the bottom. Adding hydroxide causes the hydrogen ion concentration to decrease. In the aqueous solution, we have this equilibrium constant that's always important. Remember that this hydronium ion and the hydrogen ion are the same thing. So they're always present. In pure water, those concentrations are the same. And if you look back at the reaction, it's because every time a water ionizes, you'll get one of each. Okay? And those concentrations are 10 to the minus 7th, and that's just because that's the square root of the kW. But anyway, it's a very small number. And kW does depend on temperature because it's an equilibrium constant. So I mentioned the temperature there, but anyway, so what if you have more hydrogen ions than hydroxide? Well, that can happen if you add an acid. And so that would be considered acidic. Pure water, they're equal, but when you add an acid, that happens. And if you add a base, hydroxide is greater. Okay, so we determine pH based on just this one ion. We don't have to use hydroxide because they're related. You can look at just one of the two and the other one is in relation to it. So pH is how we measure how acidic or basic a solution is, and this is the equation for it. It's the minus log of the hydrogen ion concentration. You need to know, we're going to calculate pH. You need to know that neutral is 7, because neutral is where those ions would be in equal concentrations. You need to know that less than 7 is acidic and greater than 7 is basic. We have an extra sig fig rule as well. So with a pH, because it's a log function, there's another sig fig rule for it. This front number doesn't count as a sig fig, only those. And so when I had 2 sig figs in my hydrogen ion concentration, that means I go 2 past the decimal on my pH. This is just the pH scale showing neutral, acidic below, basic above. And I just wanted to show you kind of a shortcut and something to watch for. This is a logarithmic scale, and so it has to do with the exponent of the hydrogen ion concentration. If I look at this hydrogen ion concentration, the exponent that I raised the 10 to is the pH. And as long as this number in front is exactly 1, that's true. When that number is not exactly 1, then it won't come out to exactly that. But that's basically how a log function works.